Hi everyone, my name's Jeff Dean and I'm Math Dad. I'm here to help you help your kids understand math. And today I'm coming to you with part 3 of understanding fractions. Now, before you move forward on this part, it's really important that your kids have a solid understanding of what we talked about in part 1 and part 2. So for what we're doing today, the whole is going to be a standard sheet of paper. 8.5 by 11 sheet of paper is the size of our whole for everything we're doing today. And what I'm talking about is true anytime we know for a fact that the whole is the same size for all of the fractions. And that is one of the things that we gotta make sure that our kids always ask when they're asked to do things with fractions. Is the whole for each fraction the same size? And if the answer is yes, then we can do what we're talking about tonight. Check this out. So in order to be able to do what we're talking about tonight, we need to bring back 2 words that we probably remember when we learned about fractions. The old numerator and denominator. Now, I'm going to be talking about these perhaps a little different than the way that you learned. I remember learning the numerator is the top number, the denominator is the bottom number, but there's more to it than that. Here's the thing that we need to make sure our kids understand. The numerator, which is the top number, represents how many equal-sized pieces that we have. So if the numerator is a 3, we have 3 equal-sized pieces. If the numerator is a 7, we have 7 equal-sized pieces. Now the denominator, which is the bottom number, represents the size of each piece. So if the denominator is a 4, that means each piece has a size 1/4. So think about this. If the numerator was a 3 and the denominator is a 4, that means we have 3 pieces that are each size 1/4. And it would look something like this. This is 3/4. We have 1/4, 1/4, 1/4. We have 3 pieces and each of those pieces is sized 1/4. That's what 3/4 means. So, in order to do what we're talking about tonight, we really have to make sure we have an understanding that the numerator is how many equal-sized pieces that we have, and the denominator is what size piece are we talking about. Suppose we want to know whether one fraction is bigger than another fraction. There's a couple of things that could happen. The first thing that could happen is probably one of the easiest ways to tell whether one fraction is bigger than another fraction. And that is when you look at the 2 fractions, the denominators are the same. Why does that make it easy? Because that means the sized pieces that we're talking about are the same. So for example, suppose I have a fraction that's size 3/6, and I want to know what's bigger, 3 of these 1/6 pieces or 4 of these 1/6 pieces? Well, that's pretty easy to figure out. 3 is smaller than 4, so 4/6 has to be bigger than 3/6. And why? Because I have more of them. I have 4 of them versus 3 of them. So if the denominator is the same size, then comparing is really just a matter of thinking of which one do I have more of. And if we understand that the numerator is how many of those pieces we have, it makes it pretty simple. Let's look at another one. These are all 1/8. So my question would be, what's bigger, 3/8 or 5/8? Well, 3/8 means I have 1, 2, 3 of these pieces. 5/8 means I have 1, 2, 3, 4, 5 of these pieces. So 5/8 is clearly bigger than 3/8 because I have more of them. That's one of the easiest ways to compare fractions. When the denominators are the same, it's just a matter of determining which one you have more of those equal sized pieces. Now, the second way this can happen, it can become a little bit more challenging. So let me start by asking you a question like this. Suppose I have canisters that are this size, and I have 3 of these canisters, and I'm going to compare them with 3 of these canisters. Would 3 of these be more or less than 3 of these, as far as how much they hold? Now, if you're thinking logically, well, this one holds less, so 3 of the smaller canisters would definitely hold less than 3 of the bigger canisters. And if you said that, you'd be absolutely right. This is an example of what if the numerators were the same? In other words, what if I know I have the same number of pieces, but the sizes of the pieces are different? The only thing we have to figure out is which piece is a smaller size. So let me ask you this question. If I know I have 2 pieces that are each 1/4 size, and I want to compare it with 2 pieces that are each 1/3 size, which fraction would be bigger? 2/3 or 2/4? Well, here's where some of our understanding from part 1 and part 2 are really important, because the fourths take 4 pieces to make the whole. The thirds take 3 pieces to make the whole. So thirds are bigger because it takes less of them to make up the whole. It takes 4 of these to make a whole and only 3 of these to make a whole. So since thirds are bigger than fourths, 2 of these would be bigger than 2 of these. So 2/3 is bigger than 2/4 because I have 2 of bigger pieces than 2/4 is. Let's look at another one. What if I wanted to know 3/8 compared to 3/6? Which one do you think would be bigger, 3/8 or 3/6? If you said 3/6, you'd be correct. Here's the reason why. 6ths are bigger size pieces than 8ths. Why? Because it takes less of them to make the whole. This is how big 6ths are. This is how big 8ths are. You can see 6ths are much bigger than 8ths. So 1, 2, 3/8 compared to 1, 2, 3/6. Because 6ths are bigger than 8ths, 3 of them is bigger than 3/8. So, 2 ways that we're talking right now about how we can compare fractions. There is a third thing that could happen. It could be that the numerators are not the same and the denominators are not the same. And in order to compare those, we may have to try to find some common ground. But that is going to be for another video. I'm Jeff Dean, and I'm Math Dad.